Hello. In this video, I'm going to show you how to derive the density of states for a 3D, 2D, and 1D solid. Before we dive into the derivations, the density of state is the number of different states at a particular energy level that electrons are allowed to occupy. Most often, it is also referred to as the number of states per unit volume per unit energy. With the density of state, bulk properties such as the specific heat, paramagnetic susceptibility, and other transport phenomena of conductive solids depends on it. We also use the density of state to determine the general distribution of states as a function of energy, as well as the spacing between energy bands, especially in semiconducting materials. So, for the three-dimensional case, the density of state is generally given as 1 over the volume times the change in the number of field states divided by the change in the energy. Or you simply put, it is 1 over the volume times the change in the number of field states with respect to the energy. This therefore means for us to do this derivation, we need the number of field states. And this number of field states for the three-dimensional case is given by this expression here, where this is the volume of the sphere and this is the volume of the single state. And the factor of 2 you have here is to account for the 2 possible states or electron spins you would have in this solution. You will either have a spin up or a spin down. So to get this volume of a single state, we use this expression and we end up having that this volume is given by pi cubed over the volume. Also, we get the volume of the sphere, which is commonly given as 4 pi over 3 times the radius cube. In this context, the radius is k. If we substitute this expression and this one into this, then what we are going to get is what we have here. So we can do the simplification, and what you end up having is that the number of field state is equal to the radius cube times the volume over 3 pi squared. This is in terms of K, but we will need it in terms of energy to make life easy for us to get this expression. But you can still keep it like this, even though you will still need the expression for the energy, because this expression you have here can also be simplified as follows. So you have 1 over V dN dk times dk over dE. So here you're using the chain rule to expand that expression, where you will have to differentiate this with respect to E. But I would want to do everything and differentiate just once. I don't want to do differentiation 2 times. So I start with this expression, this displacement relation, where you have E equal to h bar squared k squared over 2m. And when you make k the subject of the formula here, you end up having that your k is equal to the square root of 2me over h bar squared. Now, if you should substitute that expression for k inside the number of field state expression, this is what you're going to get. And doing the simplification, bearing in mind that the square root is raised to the power a half, then you're going to get something like this, which is this expression right here. Now we have it in terms of E, so it's easy for us to do the differentiation once. So we differentiate this with respect to E. And when we do that, we find that we treat this as constant and differentiate only this. So this 3/2 comes down, which you have it here. Then you subtract 1 here, and then you're going to be left with a half. Now that you do the simplification, because this 3 cancels with this, then you have 2 coming here. This is what you end up with. Now substituting it into the expression for the density of state, which is given as 1 over the volume times the change in the number of field states with respect to the energy. You're going to have this expression, 1 over V, which is this one, then this V over this, which is all of this. So this V can cancel with this, and you will end up with this expression here. So this right here is your expression for the density of state for a 3-dimensional solid. If you should plot this, because you recognize that this is directly proportional to the energy raised to the power a half, is going to take this nature. So here you're going to have the density of state, and then here is going to be your energy. Then the graph goes something like this. So this is the nature of the plot you will have for the density of state for a 3-dimensional solid. So let's proceed with the density of state for a 2-dimensional solid. Here, everything will very much be the same, except that instead of 1 over V here, you're having 1 over the area, because we have just 2 dimensions. The number of field states will be given now by the volume of a circle, because this will be treated like a circle, all over the volume of a single state. So everything very much stays the same, and these two also account for the 2 possible electron spins we will have. Then the volume of the single state will be given by pi squared over the area. Meanwhile, the volume of the circle will be given by pi radius squared, and k is our radius in this case. Substituting this expression and this one in here, you're going to have this, and doing the simplification, this is the expression for the number of field states you will get. This is still in terms of k. We do the same trick as above to get k. Substituting it, we end up having that our n in terms of E is given by this. Now we can go ahead to differentiate it with respect to E. So if you differentiate the energy, this also is treated as a constant. Differentiate with respect to E, E is 1. When you differentiate E, you get 1. So multiplying by this, this is what you get. So you substitute it into your definition of the density of state for a 2D solid. Then you're going to have this 1 over A, which is this, then this expression, which is this one we got here through differentiation. This A cancels out with this, and what you end up getting is this expression. What you would notice here is that the density of state for a 2D solid does not depend on the energy. So if you try to plot it, you're going to have something like this. So this is your energy, and this is the density of state. So if you try to plot it, you get something like this. So it stays constant with energy. So this is it for the 2-dimensional solid. We can now move on to the 1-dimensional solid. For the 1D solid, you have that the expression is given as 1 over the length, because we just have a line, as you would see, times the change in the number of field states divided by the energy, which is still the same thing. And the number of field states is given as the volume of the line by volume of the single state. These two also account for the 2 possible electron spins. The k-space volumes will be given by this pi over L. So the volume of the line in K space now will just be K. You substitute it just like we did in the other two cases above. You end up having this expression. Still again from the expression for the dispersion relation, which is given as this, we get our K. Substituting it, we have the expression in terms of energy. So we can simplify this further to get this expression. So now when we differentiate this, you find that this half comes down as in here. You subtract 1 from it, you're going to have negative half. So this is what you will end up getting as the change in the number of phase state with respect to the energy. When we use now our definition or for the density of state for one-dimensional solid, we will get that 1 over L in bracket, all of this. So you see that this L can cancel with this, and then you end up with this expression. This is the expression for the density of state for a one-dimensional solid. So you find that this is inversely proportional to the square root of the energy. Therefore means if we try to plot it, we're going to get something like this. So this is all what I wanted to show you regarding the derivation for the density of state for a one-dimensional solid, the two-dimensional case, and the three-dimensional case. Please feel free to leave a comment or ask your questions. Thank you.